Limits at infinity, a precise definition. Previously, what we have discussed when we looked at limits at infinity, we were able to graph functions and find their horizontal asymptotes and as well as their oblique asymptotes. Here we'll look at the precise definition of limits at infinity. We say that f of x has a limit L as x approaches infinity, and we write it as limit of f of x as x approaches infinity equal to L if for every number epsilon greater than 0 there is a corresponding number m such that for all x's greater than m it implies that the absolute value of f of x n minus L, the difference between the y and its limit, is less than epsilon. In the same way, the limit of f of x as x approaches negative infinity is equal to L if for every number epsilon greater than 0 there exists a corresponding number n such that for all x's to the left of n, okay, for all x less than n, it implies that the absolute value of f of x minus L is less than epsilon. Let's look at it graphically because we're more familiar when we look at it visually. If suppose we consider the function y equal to 1 over x and we let epsilon be given, okay, and we know that the limit of 1 over x as x approaches infinity plus infinity is 0 because it's asymptotic to the x-axis, which is y equal to 0. So how do we show that that is the case, that the limit of 1 over x as x approaches plus infinity is 0? So if we let epsilon greater than 0 be given, we are taking this band, okay, an epsilon band, where we want to find a value m such that for all x's greater than this m, and notice that if y is equal to epsilon, then solving for x, we have if y is equal to epsilon, y is equal to 1 over x. So 1 over x is equal to epsilon. Solving for x, x is equal to 1 over epsilon. So for this corresponding y, our x is equal to 1 over epsilon. And notice from the graph that for all x's to the right of m, to the right of 1 over epsilon, these y values remain within the green band. Now, if we want to let x approach infinity, negative infinity, we look at the negative side, and still the width here is epsilon. And if I want to solve for x, y here, y is equal to negative epsilon. So if y is equal to negative epsilon, then 1 over x is equal to negative epsilon. Solving for x, we just take the reciprocal of both sides. Then we have x is equal to minus 1 over epsilon. For this y, our x is minus 1 over epsilon. So the choice, naturally the choice of our n would be 1 over negative 1 over epsilon. And all the x's to the left, for all x's to the left of n, then the y values remain within the epsilon band below 0. Recall, assume that a and b are real numbers that have the same signs. In other words, it's either both a and b are positive or both a and b are negative. If a is less than b, then whenever we take the reciprocal, it reverses the order of inequality. Also, recall that another way of defining the absolute value of x is it's equal to the square root of x squared. And another rule or definition about absolute value and inequality, such that, say, the absolute value of x is greater than a, what this means is that either x is greater than a or x is less than negative a. This is just showing you the definition of limits at infinity. Okay, I'm taking this example on page 185, and we want to show the limit of 1 over x as x approaches infinity is equal to 0. And graphically, we've already seen that our choice of m is equal to 1 over epsilon. Let's see. Here we work through the solution by letting epsilon greater than 0 be given. And what is our goal? We want to find a number m such that for all x's, where for all x is greater than m, it implies that by this definition, the difference, the absolute value of the difference between f of x and its limit here, our f of x is 1 over x minus the limit L equal to 0, is equal to, of course, that's just the absolute value of 1 over x is less than epsilon. Okay, let's continue on. If I look at this, that's just, if for all x's that are greater than 0, we have that 1 over x, we can just take off the absolute value sign. For x is greater than 0, 1 over x is less than epsilon. And if I take the reciprocal of both sides, I will get x is greater than 1 over epsilon. And that's this thing, this inequality matches this inequality. So that means, what is our choice of m? We choose m to be equal to 1 over epsilon, so that for all x is greater than m, then the implication will hold that this is true. In the same way, if we want to show that the limit of 1 over x as x approaches negative infinity is 0, we let epsilon greater than 0 be given. Okay, our goal is to find a number n such that for all x's to the left of n, it implies that the absolute value of 1 over x minus 0, which is in absolute value 1 over x less than epsilon. Okay, note that if x is less than 0, then if we take the absolute value sign, it means that the negative of 1 over x is less than epsilon. Taking the reciprocal of both sides, we'll have minus x is greater than 1 over epsilon. And then multiplying both sides by negative, we'll have x is less than negative 1 over epsilon. And here, this inequality matches this, which means, what is our choice of n? We choose n to be equal to negative 1 over epsilon, so that for all x's such that x is less than negative 1 over epsilon, then it implies that 1 over x is less than epsilon, which proves that the limit of 1 over x as x approaches negative infinity is equal to 0.